on to next topic, merits of Bohr model. Now what are the merits of Bohr model? Now he could explain, first merit, he could explain the stability of atom. He could explain the stability of atom. Now according to Bohr model, electrons rotates around the nucleus in certain quantized fixed path. Electron revolves or rotates around the nucleus in certain quantized fixed path. They are known as orbits. They are known as orbits. Okay. What are quantized? Quantized means fixed energy, right? So electrons rotates around the nucleus in certain fixed path, quantized fixed path. That means they are having fixed amount of energy. Okay, path. Okay, as long as this as long as electron revolve in a fixed path, in a fixed quantized path, it will not simply lose energy or simply gain energy. It will not simply lose or gain energy. As long as electron revolve in a or rotates in a fixed path, it will not simply lose or it will not simply gain energy. So it will not losing energy means that electron will not fall to nucleus. It will not fall to, it will not collapse with the nucleus. I think it's clear. I'll explain once more. Here, according to Bohr model, electrons revolve around the nucleus. Electron revolve around the nucleus in certain fixed path, and that fixed path are known as orbits, and orbits are quantized. Electron revolves around the nucleus in certain fixed path, they are known as orbits, and orbits are quantized. What are quantized means? Quantized means they have fixed energy. Now, as long as electron revolve in a fixed energy path, quantized path, okay, it will not simply lose or simply gain energy. If it simply lose energy, what happens? In each turn, it will come closer to the nucleus and collide with the nucleus. But this is not possible because here electrons are revolving in fixed path. As long as electron revolving in a fixed path, it will not lose energy. That means that electron will not collide. It will not collide with the nucleus. It will not fall to the nucleus. Okay. So here atom is stable. According to this model, atom is stable. I think its first point is clear. This is the first merit. He could explain the stability of atom. As long as electron revolve in a fixed quantized path, it will not simply lose or gain energy. That means electron will not fall to the nucleus. It will not collide with the nucleus. I think it's clear. Moving on to the second merit, could explain the electronic configuration of the atom. He could explain the electronic configuration of atom. Now, according to him, number of electron in each orbit is 2n square. Each orbit is 2n square. Now, he could explain the electronic configuration of atom. Okay. Now, in the case of first orbit, n value is equal to 1. So, number of electrons in that orbit, number of electrons is equal to, by using this formula, he calculates the number of electron in each orbit. So, 2 into n square. Here, first orbit n value is 1. So, 2 into 1 square, 2 electrons. So, number of electrons in first orbit, 2 electron. Now, in the case of second orbit, n value is equal to 2. N value is equal to 2. So, number of electrons is equal to 2 into 2 square, n square. N value is equal to 2. So, 2 into 2 square, that is 2 square 4. 4 into 2, 8 electrons. So, second orbital there are 8 electrons. Second orbit there are 8 electrons. Now, third orbit. Now, in the case of third orbit, that is, this is K orbit, K, L, M. Third orbital is M orbit. N value is equal to 3. So, number of electrons, that is 2 into 3 square. 3 square 9. 9 into 2, 18. 18 electrons. Right. Now, fourth orbit, N value is equal to 4. K, L, M, N orbit. So, number of electron, 2 into 4 square. 4 square 16. 16 into 2, 13 electrons. So, number of electrons in fourth orbit, 32 electrons. So, he could explain the electronic configuration of atom. Number of electrons in each orbit. I think it's clear. Moving on to next merit. Next merit is he could calculate the radius of each orbit. Now, next merit is he is able to calculate radius of each orbit. Radius of each orbit. Radius of each orbit. So third merit, radius. Calculate. So he derived an equation to calculate radius of each orbit. So he calculated an equation to he derived an equation to calculate radius of each orbit. And the equation to calculate radius of each orbit is Rn is equal to 52.9. Rn is equal to 52.9 into n square by z picometer. Rn is equal to 52.9 n square by z picometer. Here n is number of orbit, z means atomic number, pm picometer. For example, consider hydrogen atom. Consider hydrogen atom. Now let this be nucleus. Now hydrogen atom contain one electron in first shell. This is the one electron, and let this be the second shell. Here there are no electrons because in a hydrogen atom there is only one electron, and that electron is present in K shell, or n is equal to 1 shell. Let this be L shell, n is equal to 2 shell, and let this be N shell, K L M shell, n is equal to 3 shell, and let this be fourth shell. Okay, let this be fourth shell, n is equal to 4. Okay, fourth shell. Now by using this equation, he calculated the radius of each orbit. Equation is Rn is equal to 52.9 into n square by z picometer. For hydrogen atom, z value is equal to 1. For hydrogen atom, z value is equal to 1. Atomic number of hydrogen atom is 1. So radius of first orbit, you can write it as R1. Radius of first orbit of hydrogen atom. In the case of hydrogen atom, radius of first orbit, let it be R1. R1 is equal to 52.9 into n square. N value is 1. First orbit. For first orbit, n value is 1. 1 square by, and z value. Z is atomic number. Atomic number of the hydrogen is 1. 1. 52.9 into n 1 square by 1, that is equal to 52.9 picometer. PM picometer. 1 picometer is equal to 10 raised to minus 12 meter. I think you remember this one. You have already studied this in first chapter, some basic concepts of chemistry. So we can easily calculate radius of each orbit of any atoms. Not only hydrogen, you can use this formula to calculate radius of each orbits of any atom. Now for second orbit radius, let that radius be R2. So equation will become R2 is equal to 52.9 into 2 square by 1. Z value for hydrogen, Z value is 1. So you'll get 52.9 into 4. Right? Now third orbit radius is equal to R3 is equal to 52.9 into 3 square by 1. For hydrogen, Z value is equal to 1. Right? Now for fourth orbit, 52.9 into 4 square by 1. Z value for hydrogen atom is 1. Now in the case of helium atom, for first orbital equation become 52.9 into 1 square by 4. Helium, Z value is equal to 2. So based on the type of atoms and orbit, you can easily calculate radius of that orbit by using this equation. So he derived an equation to calculate radius of each orbit. Third merit. I think it's clear. Now he derived an equation. To calculate energy of each orbit. Let the first energy of first orbit will be E1, second orbit will be E2, third orbit be E3, fourth orbit be E4. So he calculated energy of each orbit, or he derived an equation to calculate energy of each orbit. Okay, I'll write the equation here. I think it's clear. He calculate the radius. He derived an equation to calculate radius of each orbit. He derived equations to calculate energy associated with each orbit. He derived equation to calculate energy associated with each orbit. Okay, now I'm going to write the energy relation here. Okay, I think it's clear. I'm going to write the energy relation here. Okay, energy relation here. Now equation to calculate energy is, we can study four equation. First equation, En is equal to minus 2.18 into 10 raised to minus 18 Z square by N square joules. Z square by N square joules. Minus 2.18 into 10 raised to minus 18 Z square by N square joules per atom. Joules per atom. This is the equation to calculate energy. Minus 2.18 into 10 raised to minus 18 Z square by N square joules per atom. Now, if energy is expressed in ergs per atom, if energy is expressed in ergs per atom, ERGS, ergs per atom, then equation will become En is equal to minus 2.18 into 10 raised to minus 18 Z square by N square. Now you have to multiply at 10 raised to 7 with it, because 1 joule is equal to 10 raised to, I think you remember that 1 joule is equal to 10 raised to 7 ergs. So you can convert joules to erg by multiplying with 10 raised to 7. So equation will become minus 2.18 into 10 raised to minus 18 into 10 raised to 7 Z square by N square. I think it's clear. Now you can convert this into kilojoules per mole. In the case of kilojoules per mole, energy equation is En is equal to minus 1312 Z square by N square kilojoules per mole. So in kilojoules per mole, energy of each orbits can be calculated using this equation. Here Z means atomic number, N means number of orbit. For first orbit, N value is 1. Second orbit, N value is equal to 2. And this equation is used if energy is expressed in kilojoules per mole. If energy is expressed in kilojoules per mole, you have to use this equation. Now, if energy is expressed in electron volt per atom, then you have to use this equation. En is equal to minus 13.6 Z square by N square electron volt per atom. So based on the type, based on the unit, you have to use different relation. So based on this, we can calculate energy of each orbit. I think it's clear. This is the equation to calculate energy of each orbit. Okay. In the case of En is equal to, if energy is expressed in joules per atom, energy equation is minus 2.18 into 10 raised to minus 18 Z square by N square joules per atom. Now in the case of ergs, if energy is expressed in ergs per atom, equation is En is equal to minus 2.18 into 10 raised to minus 18 into 10 raised to 7 Z square by N square. Now in the case of kilojoules per mole, if energy is expressed in kilojoules per mole, energy equation is minus 1312 Z square by N square kilojoules per mole. And if energy is expressed in electron volt per atom, equation is minus 13.6 Z square by N square. These are the equation to calculate energy of each orbit. Okay, for example, if you consider, so I'm rubbing these merits. I think it's clear. Okay. Now, for example, if you consider hydrogen atom, Z value is equal to 1. Now, for first orbit, that is N is equal to 1, energy value in joules per atom is E1 is equal to, first orbit is N value 1, E1 is equal to minus 2.18 into 10 raised to minus 18, Z value, Z square, that is 1 square by N value 1 square joules per atom. Now for second orbit, N value is equal to 2, so E2 is equal to minus 2.18 into 10 raised to minus 18, Ez square, that is 1 square by, here Z value is 1 for hydrogen, 1 square by 2 square joules per atom. Okay, I think it's clear. These are the equations to calculate energy based on the unit. You have to use different energy equation. I think it's clear. Moving on to fifth merit, could explain hydrogen line spectra. He could explain hydrogen line spectra. So hydrogen line spectra. I will explain what is hydrogen line spectra. So he could explain hydrogen line spectra. Now before explaining hydrogen line spectra, you should know what a spectrum is. What spectrum is? Spectrum means it's a pattern of radiation of different wavelength produced on the screen when a beam of light is passed through a prism. So it's a pattern. It's a pattern it's a pattern observed on a screen. It's a pattern observed on a screen when light is passed through a prism. When light is passed through a prism, the patterns of light formed. The patterns of light formed on the screen. That pattern is known as spectrum. So patterns of radiation of different wavelength produced on the screen when a beam of light is passed through a prism. So it's a pattern of radiation of different wavelength observed on a screen when light passed through a prism. That is known as spectrum. Now there are two types of spectrum: emission spectrum and absorption spectrum. There are two types of spectrum: emission spectrum and absorption spectrum. Emission spectrum and absorption spectrum. There are two types of spectrum: emission spectrum and absorption spectrum. I'll start with the emission spectrum. Now, sunlight, we know that sun is emitting radiation. Let this be the sun. Sun is emitting radiation. Sun is emitting radiation. Now this radiation, it's an emitted radiation. Emitted. Sun is emitting radiation, and when this emitted radiation is passed through a prism, you can see in the screen there are 7 colors. You can observe 7 colors in the screen. 7 colors in the screen. You can observe 7 colors in the screen. They are violet, indigo, blue, green, yellow, orange, red. So when sunlight emit radiation, when this emitted radiation pass through a prism, you can observe 7 different wavelength or colors on the screen. This is known as emission spectrum. This is known as emission spectrum. When an emitted light is passed through a prism, then the pattern formed in the screen is known as emission spectrum. Okay. So you should know the difference. In the case of emitted spectrum, I will explain absorption spectrum later. First we can study emission spectrum in detail. When an emitted light is passed through a prism, the pattern observed on the screen are known as emission spectrum. When sun is emitting radiation, when this emitted radiation from sun pass through a prism, okay, then you can observe 7 different wavelength or colors on the screen. This is known as emission spectrum. Now emission spectrum are of 2 types. Okay, actually emission spectrums are of 3 types, but for us there are only 2 types. Okay, so emission spectrum can be classified into 2 types. Actually there are 3 types, but for us we are only discussing about 2 types of emission spectrum. So emission spectrum can be classified into 2 types. First one is continuous spectrum. Second one is line spectrum. Continuous spectrum, and second one is line spectrum. Here you can see 7 colors without any gap. You can see violet, and violet is overlapped by violet indigo, and indigo is overlapped by blue, then green, yellow, orange, red. Here you cannot see gaps between these colors. Violet, then a gap, then indigo. You are not seeing a gap in between violet and indigo. Okay, here there are no gaps between violet, indigo, blue, green, yellow, orange. There are no gaps. Here all the colors are continuously evolved. All the colors are continuously observed in the screen. All the colors are observed continuously on the screen, right? So here all the colors are observed continuously on the screen. That's why this spectrum is known as continuous spectrum. So when the light emitted from sun is passed through a prism, you can observe 7 colors, and those spectrums are known as continuous spectrum. Now those spectrums are known as emission spectrum, emitted light, emission spectrum. Now emission spectrum are of 2 types. If we are observing all the colors continuously without any gaps, those spectrums are known as continuous spectrum. Now there is one more type, and that is known as line spectrum. There is one more type of emission spectrum, that is known as line spectrum, or it is also known as atomic spectrum. Okay, line spectrum or atomic spectrum. Now consider a discharge tube. It's filled with hydrogen gas. It's filled with hydrogen gas at low pressure. Hydrogen at low pressure. It's filled with hydrogen gas at low pressure. And a very high voltage is applied across this electrode. When a very high voltage, nearly 10,000 volt. Nearly 10,000 volt. When a very high voltage is applied across this electrode, light will be emitted. Light will be emitted. Now these are emitted light. When this emitted light pass through a prism, and you will get 5 different lines. One, gap, second line, gap, third line, gap, fourth line, gap, fifth. You are observing 5 lines. You are not observing a continuous spectrum like this. You are observing 5 lines on the screen. This is known as line spectrum. Okay, this is known as line spectrum. Here also we are passing emitted light. This is the light emitted by the discharge tube. We are filling hydrogen gas at very low pressure. Hydrogen at low pressure, we are filling hydrogen gas at low pressure, and a very high voltage is applied across the electrode. Lights are emitted. Okay, lights are emitted. Now this emitted light is passed through a prism, and we are getting patterns on the screen. So this is known as emission spectrum. Now if you check the patterns on the screen, you can see 5 definite lines. Lines. One line, there is a gap in between these 2 lines. Second line, there is a gap. Third line, there is a gap between second and third. Fourth line, there is a gap between third and fourth. Fifth line, there is a gap between fourth line and fifth line. So we are not observing a continuous, we are observing a discontinuous spectrum. Those discontinuous spectrum are known as line spectrum. I think it's clear. In the case of hydrogen, if we fill hydrogen gas, we are observing 5 lines. This is known as line spectrum of hydrogen, line spectra. So Bohr is the one who explained the line spectra. 5 lines formed. In the case of hydrogen, that is known as line spectra. Bohr explained the line spectra of hydrogen. I think it's clear. So first you have to know what is the emission spectrum. What is spectrum? Spectrum are patterns of radiations of different wavelength produced on the screen when light is passed through a prism. Now there are 2 types of spectrum: emission spectrum and absorption spectrum. Now emission spectrum means emitted light. A substance is emitting light, sun is emitting light. A discharge tube is filled with hydrogen gas. When high voltage is applied, light is emitted. So the emitted light is passed through the prism in the case of emission spectrum. Okay. Now after, when we pass the light, emitted light through a prism, and if we are getting a continuous colors, continuous pattern on the screen, then those emission spectra are known as continuous spectrum. Same way, if we are getting lines, if there are gaps between those lines, that is not continuous, they are discontinuous, and if you are getting lines, those spectra are known as line spectrum. Now in the case of hydrogen, we are getting 5 lines. Okay, now actually line spectra is known as atomic spectra because for each atom the spectra will be different. For each atom the spectra will be different. For hydrogen you can see 5 lines. 1, 2, 3, 4, 5. For other atom it's not 5. It will be some other. For each atom there is a characteristic spectral lines. There will be characteristic spectra. For each atom there will be characteristic line spectra. Based on the line spectra we can identify the atom. So we can say that line spectra are actually fingerprint of atom. By fingerprint we can identify the person. Same way from line spectra we can identify the atom. Okay, for hydrogen there are 5 lines. For helium there will be different line. For lithium there will be different lines. For boron different, carbon different, nitrogen different, chlorine different, bromine different, sodium different. For each and every atom line spectra will be different. So we can say that line spectra actually fingerprint of elements. We can, from the line spectra, we can identify the element. Okay, I think it's clear. Now, I'll explain hydrogen line spectra later after discussing absorption spectra. Now, what is absorption spectra? What is the difference between absorption spectra? Absorption spectra is totally different. Emission spectra, I think emission spectra is clear. Now, absorption spectra. Absorption spectra. Now, what is absorption spectra? Absorption spectra means absorption spectra. Now, in the case of absorption spectra, here we are passing light through a substance and the substance will absorb some radiation. We are passing light radiations or light through a substance. Okay, we are passing, let it be white light. We are passing white light through a substance. The substance will absorb some radiation, and the transmitted light and the transmitted, okay, some radiations will be absorbed. From white light, it will absorb some radiation, and the transmitted radiation is passed through a prism. The transmitted, these are not emitted, they are transmitted. Transmitted, not emitted, transmitted. What does mean by transmitted? Here, for example, suppose this substance absorb, when we pass white light through this substance, if the substance absorb violet, let this substance absorb indigo, green, yellow light. The substance absorb indigo, green, yellow light. The remaining light is transmitted. Which are light are transmitted? Violet is transmitted because violet is not absorbed by the substance. Indigo, blue is transmitted. Green is absorbed. Violet, indigo is absorbed. Blue transmitted. Again, green absorbed. Yellow absorbed. Green absorbed. Violet, indigo, blue, green, yellow, orange, red. These four lines, colors are transmitted. Remaining threes are absorbed. Indigo, green, yellow is absorbed. Remaining lights are transmitted. These are transmitted light. Light which are not absorbed are not transmitted light. When this transmitted light is passed through a prism, we will get patterns on the screen. Now here, we can observe violet. We can observe violet color. We can observe indigo is not present because indigo is absorbed. So, at the position of indigo, it will be dark. Now, we can observe violet, indigo, blue can be observed. Green is not observed. Green position dark. Violet, indigo, blue, green. Yellow is again dark. Okay. Then, you can observe orange and observe red. You can observe red. Okay. This is known as absorption spectrum. Here, when we pass white light through a substance, the substance will absorb some radiation of that white light and the remaining light will be transmitted. Now the transmitted light is passed through a prism and projected on a screen. So we can observe the transmitted light. Violet is transmitted, blue is transmitted, orange, red is transmitted. Remaining colors are not transmitted, remaining are absorbed. So you cannot observe those colors. On those positions, it will be dark. This is known as absorption spectra. This is known as absorption spectra. I think it's clear. This is known as absorption spectra. Okay. Now we can say that absorption spectra is actually a negative of emission spectra. Absorption spectra is actually a negative of emission spectra. Okay. The wavelength, if you consider emission spectra, this is the absorption spectra of the substance. This is the absorption spectra of the substance. So you can observe violet, blue, orange, red. This is the absorption spectra of the substance. Absorption spectra. Now, if you take emission spectra of the substance, actually it will be opposite. That is, red is absent here, emission spectra. Orange is absent here. You can observe yellow and green. Blue is absent. Indigo, violet is absent. Actually, emission spectra and absorption spectra are actually complementary. The substance absorbed are seen in emission spectra because The substance, the color absorbed, color absorbed is obtained in emission spectra. What is emission spectra? Light emitted. Only the colors absorbed will be emitted by a substance. When you heat the substance, these colors are emitted. These colors are emitted. Okay, the colors absorbed by the substance. Okay, when the substance is heated, those colors will be liberated. So emission spectra you can see, for this substance, emission spectra you can see yellow, green and indigo. Remaining colors are absent. Now in the case of absorption spectra, these colors are absent, remaining colors will be present. So we can say absorption spectra is a negative of emission spectra, or complementary of emission spectra. I think it's clear. Okay, those radiation which are absorbed by the substance are emitted during emission spectra. Emitted light is passed in the observed in the case of emission spectra. Emitted light. So emitted light contain these three colors. So emission spectra contain these three lines, these three colors. But absorption spectra is opposite. The transmitted light, here these light are absorbed. So transmitted light contain violet, blue, orange and red. Remaining colors are absent. So emission spectra is a complementary of absorption spectra. I think it's clear. I think it's clear. Now we can discuss what is hydrogen line spectra. So now you know what is spectra, what is emission spectra. Emission spectra are of two types, a continuous, discontinuous, that is line spectra, and absorption spectra is now it's clear. Now always remember that line spectra, from line spectra we can identify the element. For each and every element, line spectra will be different. For hydrogen there are 5 lines. For helium there are different lines. For lithium different line. For lithium different line. For chromium different line. For each and every element, line spectra will be different. In the case of hydrogen there are 5 lines. Okay, so from the line we can identify the element. Okay, so actually we can say that line spectra is like fingerprint. By fingerprint we can identify the person. Same way from line spectra we can identify the element. I think it's clear. So hydrogen line spectra. Hydrogen line spectra. So going to explain hydrogen line spectra. Now hydrogen line spectra is obtained when hydrogen gas is filled in a discharge tube. Hydrogen gas is filled, hydrogen gas filled in a discharge tube at or under very low pressure. Under low pressure. Now very high voltage is applied across the this electrode. Very high voltage, nearly 10,000 volt is applied across this electrode. So hydrogen gas is filled in a discharge tube under very low pressure, and a very high voltage is applied across this discharge tube, across this electrode. So what happens is that this discharge tube will emit radiation. So it's an emitted radiation, so you will get emission spectra. Emitted radiation. From emitted radiation we will get emission spectra. Now this emitted radiation is passed through a prism and is projected on a screen. So what in the case of hydrogen gas, what we are observing is that we are getting five line. One line, gap, second line, gap, third line, gap, fourth line, gap, fifth line, gap. Okay, so this is what we are observing in the emission spectra. This spectra is known as line spectra because we are getting a group of lines, we are getting an array of lines, line spectra. Okay, now Rutherford was the one who first tried to find the reason for line spectra, but he could not find the reason. Already we have discussed in Rutherford model, unable to explain hydrogen line spectra. I think you remember. So Rutherford failed to explain hydrogen line spectra, and this was explained by none other than Bohr. By using Bohr model, Bohr explained the formation of 5 lines in hydrogen line spectra. Okay, so we are going to explain how these line spectrums are, 5 lines are formed in the case of hydrogen. We are going to explain why 5 lines are formed in the case of hydrogen in emission spectra or line spectra. Okay, so Bohr is the one who explained. So please listen carefully. Now, hydrogen atom contain only one electron. That electron is present in n is equal to 1. Here hydrogen atom contain only one electron. And that electron is present in n is equal to 1. N is equal to 2. N is equal to 3. n is equal to 4, n is equal to 5, n is equal to 6, n is equal to 7. Actually, these are circular orbits. Okay, nucleus, n is equal to 1, n is equal to 2, n is equal to 3. These are really circular orbits, but I'm going to, for explanation, I'm writing like this. Okay, these are actually circular orbits, but to explain, I'm writing these orbits like this. Okay, now in the case of hydrogen atom, there is only one electron. That electron is present in n is equal to 1 orbit. There is only one electron, and that electron is present in n is equal to 1 orbit, right? N is equal to 1. Now, here, in this discharge tube, we are filling hydrogen gas under very low pressure and a high voltage is applied. Now, when we apply voltage, when we apply electric current, what happens is that the hydrogen atom, this hydrogen gas, this is the hydrogen gas, and hydrogen gas contain lots of hydrogen atom. Lots of hydrogen atom. There are so many hydrogen atom in this hydrogen gas, right? Hydrogen gas contain lots of hydrogen atom. Now, when we apply high voltage across this electron, these hydrogen atom will get energy, electric energy. So these electron, the electron present in these hydrogen atom, I think it's clear. I'll explain once more. In this discharge tube, we are filling hydrogen gas, and a very high voltage is applied across this electron. Now hydrogen gas contain lots of hydrogen atom. Each atom contain one electron in their n is equal to 1 orbit. Each hydrogen atom contain one electron in their n is equal to 1 orbit. When we apply electric current, very high voltage, this electron, the electron present in n is equal to 1 of hydrogen atom will get energy. In the form, when we apply electric current, electron present in n is equal to 1, will get energy. So based on the type of energy supplied, based on the energy, they will move on to higher energy level. If a small amount of energy is given, they will shift from 1 to 2. More energy is given, it will shift to 3 or 4 or 5 or 6 or 7. Okay, based on the energy supplied, based on the amount of energy absorbed, okay, it will move on to higher energy level. If small amount of energy is given, it will move from n is equal to 1 to 2. If little more energy is given, it will move on to 3. More energy is given, 4, then 5, 6. So based on the energy absorbed by the electron, it will move on to higher energy level. Now, if it goes to higher energy level, actually their ground state, its actual normal level is known as ground state. In hydrogen atom, the ground state of electron is n is equal to 1. Okay, if it move on to higher energy level, if it goes to higher energy level, anyway, if it should come back to its home state, that is ground state. For example, if you are going to visit your uncle's, if you are going to visit your uncle from your home, okay, after visiting, you have to come back to your home, right? Same way, here electron absorb energy and it will move to higher energy level, but it should come back to its normal ground state or home level. That is n is equal to 1. So what happened? This electron, if it moved to n is equal to 2, it will come back to n is equal to 1. If it is moved to n is equal to 3, it will come back to n is equal to 1. 4, 1, 5, 1, 6, 1, 7, 1. If it migrate to any higher orbits or excited state, it should come back to n is equal to 1. At that time, energy is liberated. At that time, when it jump back to its normal state from higher excited state, energy is liberated. That energy corresponding to first line. In hydrogen spectra, we are observing 5 lines. 1, 2, 3, 4, 5. The first line is observed due to the energy released, due to the migration of electron from higher energy level to n is equal to 1. I think it's clear. I'll explain once more. In the case of hydrogen, electron is present in n is equal to 1. That is its ground state or home level. Now, when we fill discharge tube with hydrogen gas and apply very high voltage, energy is supplied to this electron. Electron present in n is equal to 1. So based on the amount of energy, electric energy absorbed, it will migrate to excited state. Okay, it will migrate to excited state. Now, excited state is not stable. It has to come back to its ground state. Okay, excited state, whether it's 2, 3, 4, any excited state, it's not stable. It has to come back to its ground state. So it will come back to its ground state by releasing energy. By absorbing energy, it moved to higher energy level. But when it come back to its normal ground state, it should release energy. So when it migrate back to its ground state, it will release energy. When an electron migrate from higher energy level to higher energy level to higher energy level to level 2, n is equal to 1, n is equal to 1, it will higher energy 2, 3, 4, 5, 6, 7, any higher energy level to n is equal to 1, it will release energy. That energy is corresponding to first line. That energy corresponds to first line. That energy will give the first line. Okay. Now suppose sometimes that electron will come to one state from higher energy state in 2 or 3 steps. For example, here electron is present in n is equal to 1, it will absorb energy and it will move to, suppose it will move to n is equal to 5 or 6 or something. Okay. Now sometimes it will come back in 2 or 3 steps. For example, 5 to 2, then from 2 to 1. It will come back in 5 to 2, then 2 to 1, or 6 to 2, then 2 to 1, or 4 to 2, 2 to 1, or 3 to 2, 2 to 1, or 7 to 2, 2 to 1. It can directly come from higher energy level to n is equal to 1, or it can take steps. For example, say higher energy level to n is equal to 2, then it can come to 2 to 1, right? It's also possible, right? So if an electron is jumping back from higher energy level to first 2, higher energy level to n is equal to 2, at that time they will release energy, that energy corresponding to second lines. Okay, now sometime here electron is present in n is equal to 1 ground state. By absorbing energy, it migrate to or excite to higher energy level. Now sometimes it will not come to n is equal to 1 directly. First it may come to n is equal to 3. N is equal to 3. From higher energy level, it may come to n is equal to 3. From 3 to 1. Right? 3 to 1 is possible. So if electron is migrating from higher energy level to n is equal to 3, energy is liberated. The energy is liberated. The line corresponding to de-excitation of electron from higher energy level to n is equal to 3, corresponding to third line. Now sometimes before coming to first level, it may goes to fourth level. Sometime from higher energy level, electron may jump back to n is equal to 4. From 4 it may comes to n is equal to 3. Okay, always keep in mind that direct migration, that is from higher energy level to n is equal to 1 is not possible. Always it is not possible. Sometimes it will take different step. Sometimes it will directly migrate to n is equal to 1. For example, if you are going to some your auntie's house somewhere, maybe you will spend 5 days there. Before coming back, if there is one more auntie's house, you will visit that auntie's house also, right? Okay. For example, if I'm going to Kashmir, I'm right now I'm in Kerala. Now I'm going to Kashmir. From Kerala to Kashmir. Okay. So I'm going to Kerala to Kashmir and I'm returning back to Kashmir to Kerala directly. It's possible. Now sometimes if I want to visit my my uncle's house in Hyderabad, so I'll move to Kerala to Kashmir. From Kashmir I will visit Hyderabad. Then from Hyderabad I'm coming to Tamil Nadu to visit my auntie. Okay, then I'm coming back to Kerala. This is also possible, right? So it is not important that every time a single step migration is possible. Every time single step migration from higher energy level to directly n is equal to 1. That is not important. It can come by taking different step. It can come back to n is equal to 4. From n is equal to 4, it can come to n is equal to 3. From n is equal to 3, it can come to n is equal to 1. N is equal to 2, 1 to n is equal to 1. So different steps are also possible. Electron can come from higher state to n is equal to 1 by taking different step. Okay. It is not important that always single step migration is necessary. Okay. It can take several steps. I think it's clear. Same way. So if electron is coming back to n is equal to 1 from higher state, okay, If it is not coming back directly, for example, if it is moving on to n is equal to 4, 5 to 4, 6 to 4, 7 to 4, and from 4 it is coming back to n is equal to 1, that means at that time it is energy is released due to this migration, higher energy level to n is equal to 4. That jumping will liberate some energy that corresponding to the fourth line. Same way, if electron is moving from 6 to 5 or 7 to 5, when it jump to higher energy level to n is equal to 5, at that time it will liberate energy, and that energy corresponding to fifth line. Okay, so this is how we observe 5 lines in the hydrogen spectrum. Okay, hydrogen line spectrum. I think it's clear. I'll explain once more. Please listen carefully. In hydrogen, one electron is present in n is equal to 1, or there is only one electron, and that electron is present in n is equal to 1 orbit. When you apply electric energy, this electron will absorb energy and it will migrate to higher energy level. It can move to 2, 3, 4, 5. Its ground state is n is equal to 1. It can move to 2, 3, 4, 5, 6, 7. These are all higher excited state. Now, it will come back to n is equal to 1 because its normal state, ground state is n is equal to 1. So, from higher state, it will come back to normal state by releasing energy. By absorbing energy, it move to higher state. When it come back to its normal state, energy will be released, and that energy, released energy corresponding to 5 line. That released energy gives 5 lines. Okay. Now, when electrons migrate from higher excited state, or when electron jumps from higher excited state to n is equal to 1 directly, the energy released corresponding to first line. Now, sometimes higher the electron comes to n is equal to 2 first, then from 2 to it will come to 1. From 2 to it will come to 1. Okay, from 2 to 1. So, from higher excited state, electron may jump back to n is equal to 2. From 2, it will come back to 1. So, that is also possible. So, higher excited state, electron jump from higher excited state to n is equal to 2. At that time, energy, when it jump from higher to lower, it will liberate energy. It will liberate energy that corresponding to second line. Now, when electron jump from higher energy level to n is equal to 3, again energy is liberated that corresponding to third line. When electron jump from n is equal to 4 to higher energy level to n is equal to 4, energy is liberated that corresponding to fifth line. When electron jump from higher energy level to n is equal to 5, again energy is liberated that corresponding to fifth line. Okay, all these lines have different names. First line, when an electron jump from higher energy level to n is equal to 1, then the formed line is known as, Lyman. The formed line is known as Lyman series. Lyman, Lyman series. Lyman, Lyman series. Now, if electron jump from higher energy level to n is equal to 2, higher energy level to n is equal to 2, the formed line is known as Balmer series. Balmer, Balmer series. Now, when an electron jump from higher energy level to n is equal to 3, higher energy level to n is equal to 3, the emitted radiation corresponding to fourth line, that line is known as Lyman-Balmer Paschen, Paschen, Paschen series. Now, when an electron jump from higher energy level to n is equal to 4, higher energy level to n is equal to 4, that corresponding to fourth line, that line is known as bracket series. Bracket, bracket series. Bracket, bracket series. Now, when electron jump from higher energy level to n is equal to 5, that corresponding to fifth line, that line is known as Paschen, Paschen, Paschen series. Okay, so higher energy, when an electron jump from higher energy level to n is equal to 1, the formed line, the energy is liberated, and due to that energy, one line is emitted, one line is observed, that line is known as Lyman series. Now when an electron jump from n is equal to higher energy level to n is equal to 2, energy is liberated, and due to that energy a line is observed. That line is known as Balmer series. When an electron jump from higher energy level to n is equal to 3, okay, energy is liberated, and due to that energy third line is observed, that is known as Paschen series. When an electron jump from higher energy level to n is equal to 4, the energy will be liberated, and due to that energy fourth line is observed, that is known as bracket series. And when an electron jump from higher energy level to fifth level, energy is liberated, and due to that energy fifth line is observed, Paschen series. I think it's clear. I think it's clear. Okay, now I'll explain one more thing. I think it's clear. Everything is clear. Now Bohr is the one who explained hydrogen line spectra. So this is why for a hydrogen we are seeing 5 lines. Now Lyman series, Lyman, Lyman series, higher energy level to n is equal to 1. Migration of electron from higher energy level to n is equal to 1 gives Lyman series. And Lyman series observed in ultraviolet region. Now electron jump, energy released, or second series observed, BALMER, Balmer series is observed due to the migration of electron from higher energy level to n is equal to 2. And Balmer series is observed in visible region. Balmer series is observed in visible region. Higher now, third line, that is Paschen, P-A-S-C-H-E-N, Paschen series. Paschen series is observed when an electron jump from higher energy level to n is equal to 3, and this is observed in near infrared. Lyman ultraviolet, Balmer visible region, Paschen near infrared. Now fourth line, that is known as bracket series. Bracket series, and bracket series is observed due to the migration of electron from higher energy level to n is equal to 4, and that line is observed in infrared. This is near infrared, this is infrared. And last line, that is Paschen, Lyman, Balmer, Paschen, bracket, Fund. It's Fund series. Fifth line is known as Fund series. P-F-U-N-D, Fund series. P-F-U-N-D, it's Fund, P-F-U-N-D, Fund series. Lyman, Balmer, Paschen, bracket, Fund. Last series is known as Fund series, P-F-U-N-D. Now Fund series is observed in far infrared region. Okay, last is Fund, sorry about that. It is Fund series, higher energy level. When an electron jump from higher energy level to n is equal to 5, the energy will be released, and the energy gives the fifth line, that is known as Fund series, P-F-U-N-D, Fund series, and it is observed in far infrared region. So moving on to next topic, that is how to calculate wavelength or frequency or energy of Lyman, Balmer, Paschen, bracket, Fund series. How to calculate energy or wavelength or frequency. How to calculate energy or wavelength or frequency. How to calculate energy or frequency or wavelength of line spectra of hydrogen atom. So how to calculate energy, frequency or wavelength of each lines in hydrogen spectra. Now you can use two equations to calculate energy. Or frequency. To calculate energy or frequency, you can use this equation. Delta E is equal to E2 minus E1, or E final minus E2 means final energy level minus E1 initial energy level. Okay, initial or final, or you can say that from which level electron is jumping, from which energy level electron is de-exciting or jumping jumping, and E1 is to which electron, to which energy level, to which energy level electron is jumping. For example, if electron is jumping from n is equal to 5 to n is equal to 2, then you can take this as E2. From which level electron is jumping? Here electron is jumping from n is equal to 5 to 2. And to which level n is equal to 2. So let this, you can take this as E1. Okay, so you can calculate energy and frequency by using this equation. Delta E is equal to E2 minus E1. So here E2 is from which level electron is jumping, and E1 means to which level electron is jumping. For example, if electron is jumping from 7 to 1, then n is equal to 7 is taken as energy of 7th orbit is taken as E2, and if it is jumping to n is equal to 1, then you can take this jumping, that is here to here. E2 is n is equal to 7 and E1 is energy of first shell. If electron is jumping from 7 to 2, then E2 is energy of 7th orbital minus E1 is energy of 2nd orbital. So from this equation you can calculate energy, or you can calculate frequency also by using this equation. How to calculate frequency? We know that what is delta E? Delta E is h nu. Delta E means it is h nu. H nu is equal to E2 minus E1. So nu is equal to, delta E is h nu. According to Planck quantum theory, E is equal to h nu, or delta E is equal to h nu, right? So instead of delta E you can write h nu, so E2 minus E1. So nu is equal to E2 minus E1 by h. So by using this equation you can calculate energy or frequency of each line in line spectra. Lyman, Balmer, Paschen, bracket. You can calculate energy or frequency of each line. Lyman or Balmer or Paschen or bracket or Fund series by using these two equations. Now to calculate wavelength we can use another equation to calculate wavelength. I think it's clear. Now to calculate wavelength. To calculate wavelength we are going to use another equation to calculate wavelength. No need to use this equation. You can use another equation to calculate wavelength. Okay. Now by using this equation also you can calculate what is frequency, E2 minus E1 by h, right? So what is wavelength? Wavelength is equal to C by nu. So if you know nu value, you can calculate nu value from here, then you can calculate lambda value by using this equation, that is delta E is equal to E2 minus E1. By using this equation itself you can calculate nu, frequency and wavelength. Okay, by using this equation you can calculate frequency and wavelength, but we have to study one more equation, that is to calculate wavelength. Usually we use this equation to calculate wavelength, that is lambda or wave number nu bar. To calculate wavelength or wave number we usually use another equation, and the equation is nu bar is equal to 1 by lambda is equal to RH into 1 by n1 square minus 1 by n2 square centimeter inverse. This is another equation. To calculate wavelength or wave number we usually use this equation. Nu bar is equal to 1 by lambda is equal to, what is nu bar? Nu bar is 1 by lambda. We know that. So nu bar is equal to 1 by lambda is equal to RH into 1 by n1 square minus 1 by n2 square. Here RH is known as Rydberg constant. RH is known as, here RH is known as Rydberg constant. RYDBERG, Rydberg constant, and its value of RH is 109677 centimeter inverse. So to calculate wave number or wavelength you can use this equation also. Okay, to calculate wavelength or wave number of Lyman, Balmer, Paschen, brackets, Fund series, you can use this equation. Nu bar is equal to 1 by lambda is equal to RH into 1 by n1 square minus 1 by n2 square. Here RH is known as Rydberg constant and its value is 109677 centimeter inverse. Now here n1 is from which level, n2 is from which level electron is jumping, and n1 is to which level electron is jumping. Okay. E1 is energy of the electron, to which level electron is jumping. E2 is energy of the orbit from which electron is jumping. N2 is from which level electron is jumping, from which level electron is jumping, and N1 is to which level. For example, if electron is jumping from 7 to 1, then N1 is 1, N2 is 7. From which level? N2. To which level? N1. If electron is jumping from 7 to 2, then N2 is 7 itself, and N1 is jumping to second level, N1 is 2. N2 means from which level, N1 is to which level. For example, if an electron is jumping from 7 to, not 7, 5 to 5 to 5 to, or 6 to 4, then N2 is 6, N1 is 4. Okay, so these are the two equations. You have to remember these two equations. So by using these equations, you can calculate energy, frequency, wavelength, wave number, etc. Okay, from question itself, you can understand which equation has to be used. If energy is given, energy of orbital, for example, if energy of two orbits, E1 and E2 are given, if E1, energy of two orbits, E1, E2 are given, then you have to use this equation. Delta is equal to E2 minus E1. If orbits N1, N2 are given, orbit N1, N2 are given, then you can use this equation. Okay, so based on the equation, based on the things given there, you have to choose your equation. If energy of orbits are given, then you can use this equation. Delta is equal to E2 minus E1. If orbits N1, N2 are given, N1 this much and N2 this much. If orbits are given, you have to use this equation to calculate wavelength or wave number. I think it's clear. So next topic, limitations of Bohr model. Now what are the limitations of Bohr model? So we are going to discuss 6 limitations of Bohr model. First one, it could not explain line spectrum of multi-electron atom. Bohr model could explain line spectrum of hydrogen. Hydrogen contain 5 lines, right? Now how many electrons are there in hydrogen? Hydrogen contain only 1 electron. So he could explain line spectrum of hydrogen. Hydrogen contain 5 lines. Those 5 lines are explained by using Bohr model. But he could not explain line spectrum of multi-electron atoms. For example, if number of electrons are 2, in the case of helium there are 12 lines. But he could not explain 12 lines of helium. In helium there are 12 spectral lines. Helium contains 2 electrons. Bohr could not explain the line spectrum of helium by using Bohr model. That means Bohr could explain line spectra of uni-electron atom having 1 electron. But if there are more than 1 electron, multi-electron means more than 1 electron. If atom is having more than 1 electron, he could not explain the line spectrum of those atoms. He could not explain line spectrum of lithium. Lithium contains 3 electrons. He could not explain line spectrum of boron. Boron contains 4 electrons. So Bohr could explain line spectrum of uni-electron, 1 electron atoms. But he could not explain line spectrum of multi-electron atom. He could explain line spectrum of He+. He contains 2 electron. So helium plus He plus means 1 electron. He could explain line spectrum of He+. Lithium contains 3 electrons. Li2 plus means 1 electron. 5 lines. So he could explain line spectrum of hydrogen and hydrogen-like ions. Because they contain only 1 electron. So he could explain species having 1 electron, line spectrum of species having 1 electron, but he could not explain line spectrum of multi-electron, more than 1 electron. If atom is having more than 1 electron, he could not explain line spectrum of those atoms or ions. This model could not explain line spectrum of multi-electron atoms. By using Bohr model, we can explain line spectrum of hydrogen and hydrogen-like species. Hydrogen-like species means they contain 1 electron. Hydrogen contain 1 electron. Hydrogen-like species He plus contain 1 electron. Li2 plus contain 1 electrons. Be3 plus contain 1 electron. So Bohr model could explain line spectrum of hydrogen and hydrogen-like species, but he could not explain if the number of electrons is more than 1, multi-electron atom, hydrogen spectrum of multi-electron atoms. I think it's clear. Second one, could not explain Zeeman effect and Stark effect. What is Zeeman effect? If the 5 lines, that is Lyman, Balmer, Paschen, Brackett, Funt, if these 5 lines are observed under a strong magnetic field, if these lines, 5 lines are observed under a strong magnetic field, each line will split to small lines. Each lines, Lyman, Balmer, Paschen will split to small lines. This is known as Zeeman effect. Splitting of spectral lines in the presence of magnetic field. We know that hydrogen contains 5 lines, Lyman, Balmer, Paschen, Brackett, Funt. If these lines are observed under a magnetic field, each line will split to small lines. Okay, this is known as Zeeman effect. Splitting of spectral lines. Splitting of spectral lines in the presence of magnetic field. Each line, here each line, actually here, each line split to so many small lines. Each line split to so many small lines. That is Zeeman effect. So, could not explain Zeeman effect. Bohr model could not explain Zeeman effect. And it could not explain Stark effect also. What is Stark effect? Instead of magnetic field, if the spectral lines are observed in electric field, positive, negative electric field, again you can see that each line is splitting to small lines. Okay, I can show that splitting here. Each line is splitting to small lines. This is known as splitting of spectral line in the presence of electric field. Each line is splitting to small lines. Splitting of spectral line in the presence of electric field. This is known as Stark effect. So Bohr model could not explain Zeeman effect and Stark effect. Splitting of spectral line in the presence of magnetic field. That is Zeeman effect, and splitting of spectral line in the presence of electric field. That is Stark effect. I think it's clear. These two effects are not explained by using Bohr model. Okay, Bohr model could not explain these effects. Moving on to next one. Could not explain, this model could not explain fine spectra. This model could not explain fine spectra. Now what does mean by fine spectra? Now if these 5 lines, Lyman, Balmer, Paschen, Brackett, Funt. Now if these 5 lines are observed under a sophisticated instrument, a powerful instrument, if these 5 lines are observed under a, see that each lines, sophisticated instrument, we can see that each line is made up of so many small lines. If these Lyman, Balmer, Paschen, Brackett, Funts are observed under a sophisticated, that means powerful instruments, you can see that each line is made up of so many strong, fine lines. Okay, fine lines. This is known as fine spectra. Fine spectra. So, if these spectral lines are observed through a powerful, sophisticated instrument, we can see that 5 lines, Lyman, Balmer, Paschen, Brackett, Funt, they are made up of some small lines. This is known as fine spectra. Okay, these are the first three limitations of Bohr model. Moving on to fourth one. Moving on to fourth limitation. Fourth one, Bohr model is not according to de Broglie concept of matter wave. Fourth limitation, Bohr model is not according to de Broglie concept of matter wave. The Bohr model is not according to de Broglie concept of matter wave. Now what is de Broglie concept? Now de Broglie is a famous De Broglie is a famous scientist. Now he predicted that light possesses dual nature. Light possesses dual nature. According to him, De Broglie. De Broglie is a famous scientist. He proposed he proposed a concept that is known as dual nature of matter. Now, according to De Broglie, dual nature of matter. Now, according to De Broglie, light possesses dual nature. Already we discussed this topic. Light possesses dual nature. Light possesses particle nature and wave nature. Light possesses dual nature. According to De Broglie, light possesses dual nature. Right. Light possesses dual nature. Okay. Then every moving matter should possess dual nature. According to De Broglie, every moving matter possesses dual nature, wave nature and particle nature. Every moving matter, according to De Broglie, every moving matter should possess dual nature, wave nature and particle nature. Okay, De Broglie, he introduced a concept. That concept is known as dual nature of matter. De Broglie, dual nature of matter. De Broglie concept of dual nature of matter, or De Broglie concept of matter wave. Dual nature of matter or matter wave. Now, according to his idea, his concept, every moving matter possesses dual nature, wave nature and particle nature. For example, according to him, if a bus is moving, bus is a particle. We know that bus is a particle. Okay, according to him, every moving matter is a particle. So matter possesses particle nature. But every moving matter possesses wave nature. So bus should move in wave. If a ball, if you consider a ball is a matter. So it's a particle. Matter is a particle, right? So ball possesses particle nature. But when a ball moves, it moves in a waves. That is what he is telling. Every moving matter possesses dual nature. Every moving matter. We are matter, right? We are particles. So when we move, we are moving in a wave nature. That is what he is trying to tell. I think it's clear. Every moving matter possesses dual nature. And he proposed an equation for this. Lambda is equal to h by mv. Lambda is equal to h by mv. So lambda is De Broglie wavelength. Lambda is De Broglie wavelength. H is Planck's constant. Mass of the body, mass of the matter, and V, velocity of the matter. Okay, so according to De Broglie, dual nature of matter or matter wave, every moving matter possesses dual nature, wave nature and particle nature. Matter is always particle. Every matter is a particle. Matter is always a particle. But every moving matter possesses wave nature also. And he proposed an equation. Lambda is equal to h by mv. Lambda is De Broglie wavelength, h Planck's constant, m mass of the particle or matter, v velocity of the matter. Okay, now from this equation we can see that lambda is inversely proportional to mass and lambda is inversely proportional to velocity. Lambda is inversely proportional to mass and lambda is inversely proportional to velocity, right? Lambda is inversely proportional to mass and lambda is inversely proportional to velocity. So for us, our mass is very big. Our mass or mass of a car, mass of a bus, etc. are very big, so that our mass of a ball, mass of a car, mass of a person, mass of a bus, mass is having a very big value for us. So the lambda value, wavelength will be very less. So in the case of big particle like bus, car, ball, person, etc., our mass is very high, very big, so that Okay, our mass is very large, so that wavelength will be less. So when we move, we cannot observe wave nature because our mass is very large. So when we move, when a car moves, when a bus moves, when a ball moves, we cannot observe the wave nature because wavelength and mass is inversely proportional. As mass increases, our masses is very high or very large, so that wave nature is not observed when we move, when a car moves, when a bus moves, when a ball moves. But when an electron moves, what is the mass of an electron? Mass of electron is 9.1 into 10 raised to minus 31 kg. This is a very small value. So mass of an electron is very small value, so that when an electron moves, we can observe the wave nature. When an electron moves, we can observe the wave nature. This is what de Broglie is trying to tell. When an electron moves, we can observe the wave nature. Okay, so I'll explain once more. According to de Broglie, he proposed a theory. That theory is known as de Broglie concept of matter wave or dual nature of matter. De Broglie concept of matter wave or dual nature of matter. This theory was proposed in the year 1924. Okay, de Broglie concept of matter wave or dual nature of matter. Now, according to de Broglie, light possesses dual nature, wave nature and particle nature. We have already discussed this before Planck quantum theory. So, like light, every moving matter possesses dual nature, wave nature and particle nature. Matter is always a particle. Matter always possesses particle nature. But when a matter is moved, then it possesses wave nature. This is what de Broglie explained in his equation, in his theory. Every moving matter possesses dual nature, wave nature and particle nature. And he derived an equation, and that equation is, we are not concerned about the derivation, and the equation is lambda is equal to h by mv. Lambda is de Broglie wavelength. M is mass of the matter, v is the velocity of the matter, h is Planck's constant. So according to this equation, lambda is equal to h by mv. Lambda is inversely proportional to mass and lambda is inversely proportional to velocity. So in the case of large particle like bus, car, ball, a person, etc., our masses are very large, so that wavelength will be very less because wavelength and mass are inversely proportional. Our masses are very large, so wavelength is negligible. So when we move, we cannot observe, see the wave nature because our wavelength is very small or negligible because masses are very high. But in the case of an electron, mass of an electron is 9.1 into 10 raised to minus 31 kg. It's a very low value, so that we can, very low mass, so wavelength is maximum, wavelength is very high. So in the case of electron, when an electron moves, we can see the wavelength, we can see the wave. Okay, mass is very less for an electron, so wavelength is maximum, so electron move in the form of wave. I think it's clear. This is de Broglie concept. I think it's clear. Now, Bohr model is not according to de Broglie concept of matter wave. According to Bohr, I think it's clear. Now, according to Bohr, electron move around the nucleus in certain circular path. Electron move around the nucleus. Around the nucleus in certain circular path. Right? This is what Bohr explained in his theory. Electron moves around the nucleus in certain circular path called orbit. But de Broglie says that electron always move like wave. They possess wave nature. That means electron is moving. According to de Broglie, electron is a wave. Okay, I think it's clear. So electron should move in a wave manner. But what Bohr says electron move in the fixed path. But actually electron is not moving in the fixed path. It is moving in the form of wave. Okay. So Bohr model is not according to de Broglie concept of matter wave. According to Bohr, electron move around the nucleus in the fixed path. But according to de Broglie, electron should move in the form of wave. Okay, I think it's clear. Now, this concept, de Broglie concept of matter wave, was again then proved by Davison and Germier by conducting an experiment called Davison and Germier experiment. De Broglie concept, that is electron always move in the form of wave. Electron always move in the form of wave. This was proved later by Davison and Germier, and their experiment is known as Davison and Germier experiment. From that experiment, they show that electron is a wave. Okay, so de Broglie concept is right. Electron always move in the form of wave. It was proved by Davison and Germier by using Davison and Germier experiment. So electron is a wave. So Bohr model, in Bohr model, electron move around the nucleus in fixed path, but de Broglie, according to de Broglie, it is not possible. They are waves, so they move in the form of wave. So Bohr model is not according with the de Broglie concept of matter wave. I think it's clear. Moving on to fifth limitation. This model could not explain Heisenberg uncertainty principle. This model could not explain Heisenberg uncertainty principle. Now, to understand this limitation, first we can study what is Heisenberg uncertainty principle. Heisenberg uncertainty principle. This principle was proposed by Heisenberg in the year 1927. Now, according to Heisenberg uncertainty principle, it states that it is impossible to determine simultaneously both the position, simultaneously the exact position and exact momentum of an electron, momentum or velocity of an electron. It states that, okay, fifth limitation is Bohr model is not, Bohr model could not explain Heisenberg uncertainty principle. Now, actually Heisenberg uncertainty principle was proposed by Heisenberg. So, to understand this limitation, we should know what is Heisenberg uncertainty principle is. Heisenberg uncertainty principle states that it is impossible to simultaneously determine both the position and momentum of electron. It is impossible or it is not possible. It is impossible or not possible to determine simultaneously both the position and momentum of an electron. Okay. Equation is delta x into delta p greater than or equal to h by 4 pi, or p means momentum. What is momentum? Mass into velocity. So instead of that, delta x into, instead of p you can write mv. M delta v greater than or equal to h by 4 pi. These are the two equations for Heisenberg uncertainty principle. Here delta x is uncertainty in position, delta v is uncertainty in velocity, delta p is uncertainty in momentum. Okay, this is the equation. It is impossible. Okay, delta x is uncertainty in position, delta p is uncertainty in momentum, delta v, p is actually mv. So instead of p you can write mv, m into delta v. Delta v is uncertainty in velocity, m is mass. Now this Heisenberg uncertainty principle states that it is impossible to determine simultaneously at the same time both the position and velocity of position and momentum of an electron. Both the position and momentum of an electron. Okay, we cannot simultaneously determine both the position and momentum of an electron. Okay, it is not possible to find position of electron and momentum of the electron at the same time. Okay, now what is the importance of this principle? Now you should know that if we know position and momentum at the same time, we can predict the path of the electron. We can predict the path of the electron. To predict the path of the electron, we should know position and momentum at the same time. If we know position and momentum of the electron at the same time, we can predict the path of the electron. Okay, but Heisenberg states that it is not possible to predict or determine position and momentum of the electron simultaneously at the same time. So we cannot say the path of the electron. We cannot find the path of the electron. If we know position and momentum of the electron at the same time, we can predict the path. If it is not known, we cannot predict the path. But Bohr states that electron rotate around the nucleus in fixed path. It is rotating around the nucleus in fixed path. Now the problem is Heisenberg states that it is not possible to find position and momentum of the electron at the same time. If we know position and momentum, we can easily predict the path of the electron, but it is not possible. Heisenberg stated it is not possible to find the position and momentum of an electron simultaneously. That means its path cannot be predicted. But Bohr states that electrons are revolved around the nucleus in fixed path. Path cannot be predicted if position and momentum is not known at the same time. But Bohr is predicting the path. So that is the question, how you can predict the path without knowing exact position and exact momentum at the same time. So I think it's clear. So Bohr model could not explain Heisenberg uncertainty principle. According to Heisenberg uncertainty principle, we cannot predict, we cannot determine simultaneously at the same time both the position and momentum of an electron. If you know position and momentum of the electron at the same time, we can predict the path of the electron. But we don't know, we cannot calculate, we cannot determine the exact position and exact momentum of an electron at the same time. There should be some uncertainty. If you try to calculate position and momentum at the same time, there will be some uncertainty. Values will be not certain. There will be some uncertainties. Okay. If you know that at the same time, if you can calculate position and momentum, then you can predict the path. But it is not possible. Then how Bohr is saying that electrons are revolving around the fixed path? We cannot say that. Bohr is wrong. So electrons are not revolving in the fixed path, because to find fixed path, to find the path, we should know the position and momentum at the same time. It is not possible. So circular paths are not possible for an electron. I think it's clear. Electrons are not revolving around because path is not known. So electrons are not revolving in circular path. Okay. And equations of Heisenberg uncertainty principle is delta x into delta p greater than equal to h by 4 pi, or delta x into p is mv. M delta v is equal to h by 4 pi. I think it's clear. Moving on to last limitation. Moving on to last limitation. Moving on to last limitation. Moving on to last and final limitation, it could not explain the three-dimensional structure of atom. It could not explain the three-dimensional 3D structure of atom. In Bohr consider atom as a two-dimensional, right? Because he is writing in the board, that means it's two-dimensional. Bohr, according to Bohr, atom is two-dimensional. It is not three-dimensional. So it could not explain the three-dimensional. He is not considering atom as a three-dimensional. He considers atom as a two-dimensional. Okay, he considers atom as a two-dimensional. Okay, these are the limitations of Bohr model. I think it's clear. Moving on to next model, fourth and final model, quantum mechanical model proposed by Heisenberg and Schrödinger. Moving on to next topic, that is fourth model. Quantum mechanical model, or it's also known as wave mechanical model. Quantum mechanical model or wave mechanical model. Quantum mechanical model or wave mechanical model. This model was proposed by Schrödinger and Heisenberg. This model was proposed by Schrödinger and Heisenberg. Okay, last model, and that is quantum mechanical model, and this model was proposed by Schrödinger and Heisenberg. Okay. Now, on the basis of uncertainty principle and de Broglie concept of matter wave, a new model was proposed by taking dual character of electron. According to de Broglie concept, electrons consist of two nature, wave nature and particle nature, right? So, by taking wave nature and particle nature, that is by taking a new model proposed by taking dual character of electron. Okay, dual character of electron. So on the basis of Heisenberg's uncertainty principle and de Broglie concept of matter wave, and considering dual nature of electron, a new model was predicted, and that model is known as quantum mechanical model or wave mechanical model. Quantum mechanical model or wave mechanical model. Okay. So by considering Heisenberg uncertainty principle and de Broglie concept of matter wave, and considering the wave nature and particle nature, dual nature of electron, a new model was proposed. That model is known as quantum mechanical model or wave mechanical model. Now, in this model, in this wave mechanical or quantum mechanical model, in this model, an atom, here, atom is considered in three-dimensional space. Okay, here, in Bohr model, it is two-dimensional. In this model, atom is considered in a three-dimensional. Atom is considered as three-dimensional. So, in this model, a three-dimensional space contains a small nucleus at the center. So atom consists of a small nucleus in the three-dimensional space. x-axis, y-axis, z-axis. So atom consists of a small nucleus in the three-dimensional space. And around the nucleus, there are some regions where there is probability of finding electron is maximum. Those regions are known as orbital. Around the nucleus, there are some region where there is probability to find an electron is maximum. Those regions are known as orbitals, not orbit, orbitals, orbitals. Okay, orbitals. So according to quantum mechanical model or wave mechanical model, according to this model, an atom consists of a nucleus in the three-dimensional space. Okay. Now around the nucleus, there are certain region where there is probability to find an electron is maximum. Those regions are known as orbitals. Okay, I'm going to represent that in board. You know there is one problem. We cannot represent three-dimensional board. Board is two-dimensional. Anyway, I'm going to draw three-dimensional representation. Okay. So according to this model, atom consists of a small nucleus in three-dimensional space. So let this be x-axis, y-axis, z-axis, three-dimensional space. So atom consists of it, the three-dimensional space. Okay, let this be three-dimensional. So there is a small nucleus in the three-dimensional space, and there are some regions where there is probable to find an electron is maximum. Those regions are known as orbitals. Okay, there are certain regions where there is probability to find an electron is maximum. Those regions are known as orbitals. Not orbit, they are orbitals. So here we cannot say that electrons are revolving around because we don't know the path of electron. To find the path of electron, we need position and momentum at the same time. That is not possible. So we cannot say electrons are revolving or rotating in circular path. Okay, so according to this model, atom consists of a small nucleus in the three-dimensional space, and around the nucleus there are certain region where there is maximum probability to find an electron. There are certain region where there is probability to find an electron is maximum. Those regions are known as orbital. Okay. Now there are certain other region where there is zero probability to find an electron. Zero probability. There is no chance to find an electron. Those regions are known as nodes. For example, if you consider this part, let this be the part. Here there is zero probability to find an electron. Then this part is known as node. Okay. So nodes and orbital, I'll explain once more according to this model, quantum mechanical model. According to quantum mechanical model, atom consists of a small nucleus in the three-dimensional space, and around the nucleus there are certain region where there is probability to find an electron is maximum. Those regions are known as orbitals. And there are certain other region where there is probability to find an electron is zero. There is no probability to find an electron. Okay, those regions are known as nodes. Okay, we will discuss nodes later. Okay, now we are going to discuss about orbital. So region around the nucleus where there is probability to find an electron maximum. Orbitals are region around the nucleus. Region around the nucleus where there is maximum probability to, where there is region around the nucleus where there is probability to find an electron. Probability to find an electron is maximum. Probability to find an electron is maximum. Those regions are known as orbital. This is nucleus. 3D space, this is nucleus. I think it's clear. Now, next is how to find the position of orbital. How to find orbitals, whether orbitals are the region where there is a probability to find an electron is maximum. So how can we find these regions, orbital, how can we find this region? So regions, orbitals can be calculated, or we can find these orbitals by solving Schrödinger wave equation. I'll explain that. That is our next topic. So how to find the orbitals? We are going to discuss that in next topic, Schrodinger wave equation. Now, the position of the orbitals, that is region where there is maximum probability to find an electron, these can be calculated by solving Schrodinger wave equation. Now, what is Schrodinger wave equation? Here, the behavior of an electron is described by an equation. That equation is called the Schrodinger wave equation. The behavior of an electron wave, is described by an equation. That equation is known as Schrodinger wave equation. The behavior of an electron wave is described by an equation. That equation is known as Schrodinger wave equation. Now, Schrodinger wave equation is a big equation. I am going to write the Schrodinger wave equation. Actually, this is Schrodinger wave equation. Dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square into e minus v psi is equal to 0. This is Schrodinger wave equation. Dou square psi by dou x square plus dou square psi by dou y square in plus dou square psi by dou z square plus 8 pi square m by h square into e minus v psi is equal to 0. This is Schrodinger wave equation. Now, if you are preparing for JEE, you have to study this equation. Okay, to describe the behavior of an electron, Schrodinger proposed an equation. That equation is known as Schrodinger wave equation. To describe the behavior of electron wave, Schrodinger proposed an equation. That equation is known as Schrodinger wave equation. Equation is dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square into e minus v psi is equal to 0. This is Schrodinger wave equation. Now, if you are preparing for JEE, you have to study this equation. It's very important. Now, if you are preparing for Neet, you can study the short form of this equation. Short form of this equation is h cap psi is equal to E psi. This is the short form of this equation. H cap psi is equal to E psi. H cap psi is equal to E psi. H cap psi is equal to E psi. H cap is known as Hamiltonian. This H cap is known as Hamiltonian. 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 Psi is wave function, and E is energy. Psi, PSI. This is called as psi. Psi is wave function. So, to find the orbitals around the nucleus, to find the region where there is maximum probability to find an electron, those regions are known as orbital. To find the orbital, we have to solve Schrodinger wave equation. Now, Schrodinger wave equation, he proposed an equation to describe the behavior of an electron. So, when we solve Schrodinger wave equation, this is Schrodinger wave equation. Short form of that equation is h cap psi is equal to E psi, h cap Hamiltonian, psi wave function, and E energy. Now, after solving this equation, we will get the values for, we will get so many values for E and psi. We will get values. Solving this equation, solving this big equation, we will get values for, I am rubbing this part, I will explain that one later. So, solving this equation, we will get values for E and psi. So, we know that solving quadratic equation, you know quadratic equation, right? Ax square plus b ax plus c is equal to 0. Solving quadratic equation, you will get values for x, right? Same way, solving this big equation, solving this Schrodinger wave equation, we will get values for E and psi. Okay, all E and psi values are not taken, only certain values are taken. Okay, during quadratic equation, I think you remember still quadratic equations. I think you still remember quadratic equation. After solving quadratic equation, ax square plus bx plus c, we will get values for x. We will get two values. Every time we will not take two values. Sometimes we will take only one value. Second value is wrong. We will not take second value. I think you remember. Same way, here, solving this equation, we will get so many values for E and psi. we will not take all the values. We will take only certain values. Okay, we will take certain values. There is some condition. I don't want to tell you about the conditions. We will take only, we will take some certain values. Okay. Okay. I think it's clear. So, only certain E values and psi values are acceptable. Those values are known as, those E and psi values are known as eigen, E-I-G-N, eigen values. Okay, so solving this value, we will get, solving this equation, we will get so many values for E and psi. Only certain E and psi values are acceptable. Not all E and psi values are. Solving this equation, we will get so many E and psi values. We are not taking all E and psi values, only certain values. Certain, they have to obey certain conditions. I don't want to reveal those conditions. Okay, it is not important for us. So, only certain values are taken. Okay, those values, those certain E and psi values are known as eigen values. Okay, eigen values. So I'll explain once more. First we can again discuss about Schrodinger wave equation. Schrodinger proposed an equation to describe the behavior of electron wave. Schrodinger proposed an equation to describe the nature of behavior of electron wave, and that equation is dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square into e minus v psi is equal to 0. If you are preparing for JE, you have to study this equation. It's very important. Now if you are preparing for Neet, no need to study that equation. The short form of this equation is h cap psi is equal to E psi. Okay, h cap is Hamiltonian, psi is wave function, E is energy. Now, like quadratic equation, if you solve this equation, you will get values for E and psi. You will get values for E and psi. You will get values for E and psi. Okay. Now, all values that is obtained from solving this equation, all E values and psi values that is obtained by solving this equation is not taken. Only certain values which obey certain conditions are taken. I don't want to reveal those conditions. Certain values are taken. Those taken values, those acceptable values are known as eigen values. So now we got values for energy and psi. Now we got, solving this equation, we got values for energy and psi. Now, significance of psi. We are going to study about the significance of psi. Significance of psi. Please listen carefully. Significance of psi. Significance of psi. S-I-G-N-I-F-I-C-A-N-C. Significance of psi. Now, psi just gives the amplitude of electron wave. Amplitude, A-M-P-L-I-T-U-D, amplitude of electron wave. Psi value is not significant. It just gives the amplitude of electron wave. Okay. It just gives the amplitude of electron wave. Psi value just gives the amplitude of electron wave. There is no significance for psi. But psi square has some significance. If you square the psi value, it will give the orbital. That is the region where there is maximum probability to find an electron. So the psi square value is significant. It will give the orbital of an electron, orbital around the nucleus. Okay, it will give the orbital around the nucleus. I think it's clear. So Schrodinger wave, I will explain once more. Schrodinger wave equation. When we solve Schrodinger wave equation, we will get values for E and psi. All E values and psi values are not taken. E and psi values which obey certain condition. Okay, they are taken. They are known as eigen values. Eigen values. E-I-G-N. Eigen E and eigen psi values. Now, psi value. What is the significance of eigen psi value? They have no significance. They just give the amplitude of electron wave. Amplitude of electron wave. Height of electron wave. But when you square this psi value, when you square the psi value, it gives the orbital. What are orbitals? It is the region around the nucleus where there is probability to find an electron is maximum. So, solving psi square, we will get the position of the orbital. We will get the position of the orbital. We will get the position of the orbital. So to get the position of the orbitals, first we have to solve Schrodinger wave equation. So we will get eigen E and eigen psi value. Now psi value is not, it just give amplitude of electron wave, but when you square the psi value, it gives the position of the orbital, or a position where there is maximum probability to find an electron. I think it's clear. So according to quantum mechanical model proposed by Schrodinger and Heisenberg, an atom consists of nucleus in three-dimensional space. Around the nucleus there are certain regions where there is probability to find an electron is maximum. Those regions are known as orbital. Now how to find the position of orbital? By solving Schrodinger equation. By solving Schrodinger equation, we will get the values of psi. Psi just give the amplitude of electron by, but when we square the psi value, we will get the position of orbital. I think it's clear.